Hi, it is project number 1, Newton's method for finding zeros and extrema. In this project, you will implement Newton's method to find zeros and extrema of functions. Let's define first two functions, f of x and g of x, on closed intervals, and we'll add one more function based on your student ID. Let your ID be 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the first digit will be used here at this position, and second digit, and third digit, and so on. So you can define this function I based on your ID. We will call it the ID function. So the ID function is unique for you. So you will work on the project with these three functions. Here, for f, g, and I, so three functions, you have to find all zeros, and you have to find the local and global extrema for f and g. To find the local and global extrema, you have to find the zeros of derivative of the function, and you can make a derivative for I. However, I'll ask you only the derivative of these two functions f and g. So for the zeros, you have to do you have to find the zeros for all three functions, but you can find the local and global extrema for only f and g. The Newton method is introduced to find the zeros of functions so that you can use it to find the extrema. If you apply the Newton's method for f prime of x equals 0, then result will be the critical points. At critical points, you can measure the function value, then there can be local extrema, right? Okay, here we have some details. Number 1, implement Newton's method. And I'll give you some code below. And for zeros, for each of the functions, you may start with a plot and try to get initial approximation for each zero and apply Newton's method to approximate the zero accurately. And for example, in 10 decimal accuracy, and you can add the point to the plot to see if your computation is correct. For local global extrema, now for each of f and g, you may do almost the same. First is plot, and now try to recognize where local extrema are located, and find the derivative. And for derivative, you can apply Newton's method. Of course, you have to here initialize. You have to get good initial value of 0 of the derivative. Then result will be a critical point. And also here you can find local extrema and try to add the point to the plot to see if your computation is correct. You have to report your work and results, including code and plots. Okay, here we have example. Now, I made this ID by using random calling 674029185. For that ID, the corresponding function I using this formula makes that figure. And you can find initial value around here minus 0.5 and 0.5 and around 1. And now for that one, you can choose 1.5, but I chose 1.4. And along with this 4 initialization, for each of initialization, I applied the Newton method. Here we have a code here. Okay. And that's your ID. And now you collect the digit along with the space here. And now function I will be defined in this way. And here you have to make a plot to see where the zeros are. And for that one, from this figure, I found that here the initial values for 0 are minus 0.5, 0.5, 1, and 1.4. For that, here, Newton iteration is applied along with tolerance 10 to the minus 10 and maximum iteration 100. And I put large number, but practically less than 10 iteration, it will converge. And the output is a good approximation of the zeros, and now number of iteration done inside of the algorithm. And for that, I here now print out x, and then the number of iteration, and here I of x. That is the algorithm, Newton diff iteration. Input is now function and initial value and tolerance and etmax. Along with that, here x0 is saved into x, and then that is df will make here the f prime x basically. That is good approximation, very accurate approximation of f prime at x. Okay. So here correction term will be f of x divided by df, and correction is subtracted to get new iterate. And once correction in modulus is less than tolerance, then stop and return, so that here x and it will be the last updated x and the iteration count, and that will be here now printed out. That is the result. Okay, let's see the code. Okay, here I saved it here in project ID Newton, and you can use Octave rather than MathTalent. Octave is a free version of MathTalent. Okay. Here, there's ID, and I is defined in this way, and this portion is about plotting, but in lecture note I eliminated, but you can implement this portion. And now tolerance and etmax, and along with here the initial values, I found this one along with that portion. Okay, if I execute, then the figure is given in this way. So that is exactly the same figure in the lecture note. Okay. Now, so initial values are made, and through Newton iteration, we can find a really good, very accurate the zero, and that is print out. And here you can see that is executed result. Now there are 4 zeros, and now number of iteration is 4, 5, 4, 4. And at the moment, and from left end, now I of x is 0, 0, and third one, fourth one, these values are practically 0. Okay, so it's finding very well, anyway, working very well, along with only 4 or 5 iterations. Okay, that's project number 1, and for remainder part, you can do it very nicely. Okay, have a nice day. Thank you.